Hello everyone. Today we'll tackle some spectrum of mass spec and infrared spectroscopy. Alright, first let's take a look at this mass spec. Which one of these compounds gives this mass spec? Pause the video and try to figure it out. Here are the structure of the compounds: hexane, that 2-methylpentane, this 3-methylpentane, this 2,3-dimethylbutane, and it turned out that they all have same formula. They're just a different compound. In terms of isomerism, they are all regioisomers with the different connectivity. First, I would check the molecular peak if it is. Let's see if 86 signal is indeed M peak. Okay, I corrected the formula, right? 2, 4, 6, 8, 10, 12, and then 2 end hydrogen, 14. And that's the alkane. 2 times 6 plus 2, so 14, and that makes a molecular weight of, roughly speaking, 86. So indeed, this is your molecular peak. Then you examine the isomer peaks, and the M+1 is not significantly big, and there's no M+2, meaning there's no heavy atoms. I mean, obviously there's no heavy atom, but I'm just trying to tell you, to remind you. And also M-1, the aldehyde, presence of aldehyde, right? After losing the hydrogen of aldehyde, it's not also not very significant, so there's no aldehyde, I guess. Obviously there's no aldehyde. Then you have a base peak during the analysis of the fragmentation. The best one that explain this phenomenon will match the structure the best. So let's examine the fragmentation. First, I find M-15. And the 15 is when the compound is hydrocarbon like this, it is loss of CH3. Then we notice that there is a loss of 28. Therefore, after losing from the molecule 15 followed by 28 loss gives you 43. And when you look at them, this compound can lose 15, and 28 is 2 CH2s, so 1, 2, you can lose that. And that portion is a C3H, 3, 5, 7 hydrogens, so that adds up to, let me see, 12 times 3 plus 7, so 43. So this can be, just in terms of numbers, right? This molecule also can lose methyl and lose 2 CH2s, and this also has a C3H7, so 43. Possible. This one though, you cannot lose 28. You can lose methyl, then there is a CH2, but you cannot just lose this. If you're gonna cut here, you lose this much, right? So if you try cutting everywhere, losing methyl, and then trying to lose 2 units of CH2, that's not possible, so you exclude this. And when you look at this, also, you cannot lose, after losing CH3, any of these, you cannot lose just 2 CH2s, so that's not possible. So you can see that if you analyze the fragmentation of the mass spec, you learn that mass spec is not just to get the molecular weight. It's more informative compared to the IR, especially the compound with a no polar functional group. If you run IR of these compounds, they look awfully similar. Then which one of these two fit into this one better? So after losing 15, this molecule get the plus charge on this carbon, right? After losing this 15, it turns out to be a primary, okay? And then you lose 28, you lose 2 more unit of carbon, and you break off here, and you will still get the primary carbon. So there is no reason for 43, which is this unit, to be more stable than just after losing the unit you get after losing methyl group, same primary. So why would this has to be more stable to give more abundance as ion while they are flying through the analyzer, right? So that doesn't fit in good. But hold on and not make a decision yet. But here, when you break here, you get the primary carbocation. But when you lose 2 more CH2s, loss of 28, you get the secondary carbocation, and you know this is the 43 with the most stability, and this can be obviously your base peak. So this molecule fit in to this spectrum the best, so you choose this to be your best guess. Therefore, your answer is 2-methylpentane. Now you have 2 compounds. The question is simple. You ran some reaction, like a halogenation, and which spectrum is your product when you did chlorination? That's all, which means they don't tell you what alkane they used as a reactant. But you know, in order to find out the presence of those good leaving groups, halogens, you need to pay attention to the isotope peaks, especially M2 peaks, right? So here you see twin tower, like M plus 2. There you see M and also M plus 2. There's no significant M plus 1, but here you have a little M plus 1, M plus 3, but they're not so significant. But the ratio of these 2 isotopes is about 1/3. That's about equal. So you know this compound has chlorine and that compound has a bromine. Then you can even figure out what exact structure or formula of this compound you synthesized, or even what was the reactant. If the question they're asking is, when this is the product mass spec, what was the reactant in the chlorination, right? That means, when chlorine has 2 isotopes of 35 and the 37, this peak is the one that has R group with a chlorine 35, and that peak is the one that has the same R group with the chlorine 37 isotope, and in the nature 35 is 3 times more abundant. And if you calculate the molecular weight, then neither 64 or 66, it's going to be average of the 2. I'm just going to remind you that. So when you deduct 35 out of 64, right, you get 29. Here as well, if you subtract 37 out of 66 n plus 2 peak, where you find the 37 isotope, you're gonna get 29. So 29 is, as we practiced formula analysis, if you have one carbon, then you have to have a lot of hydrogens, right? Because one carbon is 12. To make 29, you need 17 hydrogen. So on one carbon, 17 hydrogens is unbelievably too much. So if you think of two carbons, it's already 24. So you need only 5 more. Then you attach chlorine. Then you can figure out what the structure might be. So with the 2 carbon, if the molecule was an alkane, 2 times 2 plus 2, and the chlorine need to reduce 1 hydrogen in order to put chlorine, 1 each chlorine, right? Then the formula would be C2H4 6, so 5 Cl2. So that's what it is, meaning this is a regular one. And everyone knows because it's only 2 carbon, but let's assume that the carbon number is more than coupled, then you need to actually go through this process, right? So it is actually CH3 CH2 chlorine. So that's how you figure out, meaning that the chlorination reactant, if the question was asking you that, something like this is the condition. As you know, the reactant is ethane. Okay, take a look at this mass spec, and they're telling you this is ketone. They can just say this is ketone, or they can say there is IR absorption at 1722 reciprocal centimeter or something like that. They can say that instead. After you learn NMR, they can give you information of NMR. Carbon 13, they found 185 ppm, something like that. So there are a number of ways of giving you a hint that this is a ketone. Anyway, knowing this is ketone, let's figure out formula. Okay, so you gotta have some number of carbon, some number of hydrogen. Say you have a 1 oxygen. Then in order to fit it into the 86 with the 1 oxygen there, you have to subtract 86 minus 16, so 70, right? How many carbon is good to make up 70 with a couple hydrogens? If you think of 4 carbons, right, that's already, let me see, that's 48. So to make up 70, you need about 22 hydrogens. But you cannot have 22 hydrogens on 4 carbons, so that's not a good number. If you have 5 carbons, that's 60. Then you need 10 hydrogen, and that's doable. So let's go with that for now. So 5, 10, right? What if you have a 6 carbon? That's a 72 already, so not good. So it must be 5 carbon if you have a 1 oxygen, okay? That if this assumption fit into these, then we're okay. Then you figure out how many double bonds or whatever you have. So index of hydrogen deficiency or degree of unsaturation, you need to figure out. So let's see, 5, 2 times 5 plus 2, and oxygen don't change. So the formula for alkane, straight chain alkane, has to be 12. Therefore, the index of hydrogen deficiency is you're losing 2 to make up this original formula. So 1 mole of a hydrogen molecule. So you have an index of 1 degree of unsaturation, meaning you have 1 double bond or a ring, 1 ring. Other than that, you have a straight chain with the potential branches. Then they told you that this is a ketone, so it must be not the case for a ring. So you should not draw ring structure as a potential answer. It must be double bond, and the double bond is not, again, it's not a carbon-carbon double bond, right? It is a carbon-oxygen double bond. So you used up everything. Then with the 5 carbon, not aldehyde, but ketone. There are a couple of ways of making isomers. So 5 carbons, you can put ketone there or there. These are the only two. And here, your skill of making isomerism come in handy. You can think of a 4-carbon backbone, and there is only one way of making this 4-carbon backbone ketone. Not here, not here, but either one of these two, right? Wherever you put, they are same thing. So let's say I put it there. Then the one additional carbon I need to add, but I don't want to add here, then it's going to be that. And I don't want to put here because then it's going to be there. So only one place is there. So these 3 are the possible ketones you can think of, and see which one fit it into the spectrum the best. So we assumed, we are given that 86 is the molecular peak, and there's no special atom. That's what we did, right? We just put one heteroatom oxygen, and then the fragmentation analysis there is 29. So this M-29 peaks, you lose 29, and it should be quite stable peak. So this 29 is obviously CH3, CH2, 15, 14. This one cannot lose 15 and 14. 15, 15, 15. There's no 14. There's a 13. This one can lose 29. This can lose 29. All right. So then which one is more stable after losing 29? Both can be answers, but there is a well-known fragmentation mechanism that you have to apply. So in ionization chamber, you lose electron from the oxygen, like we talked about the mechanism. Then you can go through cleavage. But I hope you remember that if you have a heteroatom, you usually break on the alpha, right? But the alpha, they are double bonds, so not easy to break. Then you can break the alpha bond here homolytically. So both can lose alpha. And this can also lose alpha, so let's try. The mechanism would be then ethyl group, the 29 is lost as a radical, so not detectable. Then the other one as gaining 1 electron, the radicals pairing up, and you make up, excuse me, it should be linear. So there you have 57 peaks. That's not too bad. It's kind of stable as well. This one also can do same mechanism. Then as you can see, you lose more than 29. You lose a propyl group, which is, and the propyl radical that's not detectable is 43, which don't have a 43. But this one that's detectable out of this alpha cleavage, homolytic alpha cleavage, should give a detectable 43. You remember one of the common acetyl group? It's absent, meaning this is not the answer. This gotta be your answer. But I want to introduce one more fragmentation method for carbonyl group. You can do that if you know radical, so I didn't talk about it, and I didn't think this is necessary for undergrad student, but let's just try. My PhD thesis is on the carbonyl group, and you can see so many organic compounds have a carbonyl group in it, so it's one of the major functional group, so I think it's good to know. So what happens is this radical, I'm going to use green, can react with the close hydrogen. So hydrogen make a bond with the oxygen, then oxygen becomes positive. Then this can go here. Then one of these two electrons come over here, and the other can go here. All right, that makes one of the pi electron come here, then the other electron goes to the oxygen. So eventually you are breaking a bond there and then there. So hydrogen goes there, and then this unit becomes double bonded unit after losing the carbon here and then hydrogen there. So you're losing this as a neutral compound, ethylene group, CH2, CH2. Okay, 28. You're losing 28. But we never have a 28 loss, so we know this is not the answer. It's quite close to this, but it's not the answer. Anyway, here you broke the double bond, oxygen became this, and then it was a positive after given away and formed bond with the hydrogen, but you gain one more electron, so now it is also radical cation. There you have a double bond. Then some of you, I hope you remember, this enol functional group can go to keto group, right? So enol tautomerization will give you this type of a radical cation as well. They are in the tautomerization. But either way, the molecular weight of this ion after losing 28, this is a 58. So close, but that's not the best fit. This gives you best fit. Did I make a mistake here? Okay, let me confirm this number. If you calculate it, it's actually 57, that peak. I don't know why I put that, but yeah, so my addition is poor. Excuse me for that. So this is your answer. We knew that already, but I just gave you some more insight about the fragmentation. Hopefully now you're ready for combined problems. Here is your first combined problems. There's IR, there's a mass spec, and they didn't give you a formula. And so first we have to assume that this peak 100 is our molecular peak. If everything works out smoothly, then that's how they planned. So what else can you say? Before I get into the analysis of the mass, I want to get idea of like what atoms I have. Look at the satellite peaks for isotopes. M+1 is quite small, and there's no M+2, so we don't have any halogens. We don't have any heavy atoms like a sulfur or phosphorus and those. So it's mostly regular atoms. Nearly, around 99% of the major isotope atoms like carbon, hydrogen, oxygen, nitrogen, those things. And also when you look at the IR, this area below 1000, there's no strong peaks. So there's no halogen, obviously. What else you have? Well, these are the CHs. All right. And this 3500, it's too small to be NH. It's obviously not NH2, but it's not even NH. It's too small. 1722 is telling you that there is a carbonyl group, meaning that you have one oxygen in it. Nothing else. So I can assume, okay, let me use the red pen. Assume that we have a certain number of a carbon and certain number of a hydrogen we need to figure out to make up 100 of molecular weight, but we have one oxygen there, and oxygen do not change the molecular weight. So only the R group portion, after deducting the atomic weight of the oxygen from 100, with the carbon and the hydrogen, you need to make up 84. So we need to analyze the formula. If you have 8 carbon, that's already 96. So more than 84, not good. How about 7 carbons? That's 84, exact 84. So you have to come up with a compound without any hydrogen. Less likely for now, out. What about 6 carbons? Well, that's we did a couple times. It's a 72, and then we can have 12 hydrogens. That makes up 84, so that's acceptable. Then how about 5 carbons? That's a 60. That means you gotta have a 24 hydrogen, and that's too many for 5 carbons. Maximum you can have on the 5 is 2 times 5 plus 2 is 12. So it's twice more hydrogen. So not good. So most likely it's this. You never know, it could be the answer, but I don't think so. But anyway, we take this most likely answer. Therefore, you gotta have formula now, C6H2N, so 12 plus 2, 14. If it is what? If it is, sorry, not 14. We found out, right? So 12, so it's not 14, I'm sorry. So what I was gonna say is, if it is alkane, it's gotta be 14. So out of this, degree of unsaturation is 1. That means you must have a 1 ring or 1 double bond. Before we worry about whether the double bond is a CO double bond or CC double bond, we found the CO double bond already. So we found the use of the unsaturation. That means the rest of the molecule has no ring structure, straight chain, no pi bond at all. And we just see the rest of the CHs and bending vibrations. And this number is kind of concerning because it's over 3000. But we're not supposed to have any other double bond, and we are lack of anything around 1600. So this maybe is not alkene peaks, the CH on the alkene, right? So keeping that in mind, there could be the case, the molecular peak is not really 100. Who knows? So let's take a look at the fragmentation. So here you lost 15. Here So we lost 15 and we lost 14. Then we lost 13 to make up 58. So out of the M, 15, 14, 13, if this is a sequential loss of one chain, then it is the order. That's the order of loss. But it could be one big loss of 42 from the other part of the molecule. Okay, so that means let's go with this assumption. Okay, so sequentially, if we lose CH3, then CH2, then CH, after losing that, whatever remains here should be 58. And also, if it's a sequential, you gotta lose 15, right? So negative 15, which is a methyl group, this becomes 43. Now also in 58, 43, you must have ketone, not aldehyde, meaning you must have this here. That's a minimum thing required, and you have more carbons. Okay, so including these, minimum C2, and how many H's there? 3, and oxygen. Minimum this. You gotta make up 43, and with one more additional methyl group, you have to make 58. So you know there is one more methyl group. So these together with the additional thing here, right? That's a minimum thing required in this structure because it is a ketone. That's a minimum thing. So let's come up with a formula to make up 58, adding, CH3 methyl group, I'm sorry. So 58 with one oxygen in it, right? Then 58 subtracted by 16 is 42, only with the carbon and hydrogen. So we can assume that we may have 3 carbons. We already need 2 minimum and 1 methyl group, so 3. Let's go with that and see. How many hydrogens? $58 we want to make this peak. So the formula we are trying to make should have a minimum 3 carbons, okay? Then without oxygen, I have to make up 42. If we want to have, 3, if go with the 3, the carbon's already 36. So then hydrogen we need is a 6. And what a coincidence, right? We have 3 proposed as a minimum, and we lost methyl from here. So altogether, actually add up exactly to be 58. But dilemma here I can see right away is this is an acetone. Actually, like CH3 to be ketone, you need that, and then methyl group. So they're fully valenced unit. So how would you connect this there? You can't. Doesn't make any sense, right? But you notice here, this carbon has only 2 hydrogens. Sorry, 1 hydrogen, not 2. So what if we do this? And add 1 hydrogen here after taking 1 from there. Then this unit is not going to be 58, right? It's 57. So you may say it doesn't make sense. But remember, chopping, right, in the fragmentation, it's not just a plainly chop, chop, chop. There is an elimination mechanism. There's a lefty mechanism where you chop, further beta. So when there is an oxygen lost electron in the ionization chamber, you can lose alpha cleavage here. So you can try this radical, thinking that this can react and you need to remove, right? Then this can move. Then you like to break here, but as you can see, you cannot break. You need to probably break there, like this, alpha cleavage, right? So you're not going to be able to lose proper amount to get 58. What you get is 43 by alpha cleavage. So there's a trouble. Then probably it's not sequential loss. It's not 15 after 14 after 13. It maybe is a loss of 42. Okay, and that's not even 42 you detect, that's a 43, which is this one. So that one probably is formed by alpha cleavage. That's quite simple. These two electrons, when radical come down, you form triple bond, and this goes as a radical. You lose the whole thing. Then you get 43 cation. And we saw this mechanism before. So, forget about losing this hydrogen, right? Let's do it over here. See, you can lose 42 at once out of this. So what is the remaining mechanism for carbonyl group? I drew the molecule this way to show the fragmentation mechanism. You see the oxygen radical. That oxy radical now is abstracting hydrogen, the gamma hydrogen. Then one of these electrons go there and bringing in this one. Then this one goes to the double bond area, and this come into the double bond area, and that goes to the radical. We form the radical. Then this reaction, the radical reaction, intramolecular radical reaction, is giving you CH, not CH2, double bonded CH2. Then you get fragmentation right there. You break the bond, you get this double bond formed, and then OH, eno, and you get the cationic radical, and that goes to the keto form. I mentioned it before. And as you can see, you have acetone that's corresponding to 58. And this here is a C3H6. And C3H6 is 36 plus 6. So 42. So you lost 42 at once, not sequentially. Here you have a 15, 14, 13, but it's not sequential, right? So if you listen to the first video about the spectrometry, I kind of hinted that it's not always a sequential. It could be the big chunk. And this unique mechanism, you don't do alpha cleavage as a homolytic or heterolytic, or you don't remove this hydrogen and do elimination. But this is a fourth type of a mechanism I didn't mention, but a few minutes ago I talked about this. This is devised by a professor at Cornell University, McLafferty. Rearrangement. Very useful for carbonyl. And now you are able to explain this by losing 42. Then the 43 is from the alpha cleavage. So your product that fit into these two is this compound, which is a 2 hexanone. 2 hexanone is your hexatuone is your compound. One big lesson for you is couple signals like 1722 is not quite good number for ketone, right? This is like a borderline. It could be ketone aldehyde or acetate. Also, this peak here is slightly over 3000. This could be sp2 or spch stretching, but it turned out that it wasn't the case. But it could be the case. What do I mean by that? These ketones can actually be in the equilibrium, I mean more keto form, but they could be in enol form. Okay. Then you have sp2s. So you may have to look into it more, but anyway, you should not always go by the number precisely. That's the lesson you get. Okay, this last problem we're gonna tackle here. We're gonna see more combined spectrum problem solving later on as we cover other spectrum. But here what's happening is this is data you get from so-called reactor IR. You are able to measure the IR spectrum of a range you like to while you are running a reaction. So during a reaction like SN2E2, a certain functional group is removed, therefore the intensity becomes weaker, and then some other functional group that you are forming as a product, they are growing. So on this axis here you see the hours. As time passes, the signal intensity changes. Some are remaining constant and some are growing, and I don't see anything decreasing here. So I think you're looking at, for this spectrum, you're looking at the range of the frequency where you find your product. So you are monitoring the formation of the product. So if you can convert the height, the absorptivity to the concentration, which you can using Beer's law, A equals absorptivity equals epsilon times B, the cell size, times concentration. So you can actually do it by measuring epsilon value of each peak. Then divided by the concentration, divide the concentration by the hour, you can measure reaction rate this way using IR. So what is actually happening? As you can see, this peak is growing. So you see the number, it's 2200. So you are forming triple bond. You didn't have triple bond, now you're forming it, right? At the same time, you see 16 something, right? It's not 17 quite. And you're forming that signal, greatly. So you are forming probably CC double bond. And this peak here, a very high number for carbonyl group, it is still remaining there. So you are probably doing some elimination reaction. You're forming triple bond and double bond. Hopefully, this gives you some insight about how the scientist is using IR in the actual research. So with this, I'm gonna wrap up infrared spectroscopy and the mass spectrometry for now and move on to the NMR. Then we'll see more and more exercise problems with all of those three. So please remember, in order to be good at mass spec, you need to be good at formula analysis, and then you should be also good at radical reaction mechanism, and there are some others. And I hope you enjoyed it, and I'll see you next time.